Okay, so the final example, we will try to plot the frequency response of this transfer function. So this is the transfer function of V out over I in of this circuit. Now you can get that from performing Laplace transform analysis on a circuit. So this is the transfer function. Now let's try to write that down in the Matlab. So 10 S2 S3 10 S2 S3 okay, divide by S2 S squared plus 8S plus 10 S squared plus 8S plus 10. Okay, so here dot multiplication, probably okay, and so you can go to search in Matlab, search in Google, find out what's the difference between dot multiplication and just a simple multiplication, dot division and with a simple division. Check in Google, see what's the difference between the dot and the normal one, right? So S is the J times omega, but however you don't use J in Matlab, you use 1i. Omega equals to 2 times pi times f. It's just the frequency. Let's just 1 to, it really depends on the circuit what it looks like. All right, 0.01 up to 10 maybe. Let's just put some value and see how it looks like. All right, so that is the transfer function. What is the x-axis? That is the angular frequency. Hang on, the absolute hs, so hs, right, and then the phase of hs, you want the angle hs, but this will give you the value in radian, so we have to times 180 and divided by pi to get the value in angular. Right, so the absolute hs, let's try to plot this first. Alright, so get some error. Use dot power, say here, where is it, line? Any more error? No. Okay, so this is the frequency response. Alright, let's try to plot this in log scale. Okay, so here I have changed the frequency. Okay, instead of writing the frequency equals to whatever value and omega equals to 2 pi f, here I'm just use omega and define the value for the omega, the angular frequency. So here I use the log space. You can just simply double click this, highlight the log space, and then go to help on the go to the help, so it will show you how to use the log space. So log space a comma b comma n. So a b is actually refers to a to the power of 10 to the power of a, 10 to the power of p, and how many points? That's n. N is the n points. Alright, so here 10 to the power of 1, 10 to the power of 2 for 100 points. Okay, so let's see. So that is 10 to the power of 1 to 10 to the power of 2. So from here to here we have 100 points, 100 points. Here, or you can reduce it to 10, just 10 points, but that will not give you smooth shape, right? It's better to go with higher points, but not too much, because it will just slow the computer down, right? So that is it. You can increase this to 3, and you can reduce it to maybe -1. Forgot to increase this to 100. -1, right? This is 10 to the power of 1, that is 10. 10 to the power of 0, that is 1. 10 to the power -1, that is 0.1. Alright, so this is the frequency response. Don't forget with the X label. What is the X label? Frequency in radian, right? Y label, absolute value of the HS. Alright, there's no unit for that. And then let's draw the phase. Okay, frequency radian, that's the phase in degree. Alright, so that's the frequency response of the transfer function. Okay, now if you're just curious, maybe you can increase this to 10,000 and further reduce this to -5 and probably 10, just to see what happened on the response at a much higher frequency region. Alright, so nothing much. Basically all the signals are more interested in this region. Alright, so I'm sure if we continue to increase the frequency, we will only get a straight line. So the best way, the best region to show you the plot is between here, which is this 10, 0, 1, 2, 3, 0, 1. Okay, 3, 1. Okay, yep. So that's the frequency response of the transfer function.